Hello everyone, my name is Shishodia and today I will be presenting my case study on PowerPC. So coming to the first part, which is the architecture overview of the PowerPC. So PowerPC is a RISC-based processor architecture was created by IBM, Motorola and Apple. It uses simple, fast instructions, all 32 bits long, which makes fetching, decoding and pipelining very efficient. It follows a strict load store model. So only load and store instructions accesses memory, while all other works happen in its larger register set of 32 general purpose registers and 32 floating point registers. This reduces memory access and improves speed. PowerPC also supports parallel execution, making it great for graphics and scientific tasks. It powered Apple Mac from 1994 to 2006, and consoles like Xbox, PS3, Nintendo Wii, etc. And it still is used in embedded systems for its reliability and predictable performance. Now, coming to the instruction set architecture of the PowerPC. PowerPC is a PowerPC ISA is a instruction language of the processor built on clean and fast RISC design with all instructions 32-bit long for simple decoding and efficient pipelining. It uses multiple instruction formats: D form for load, store, and immediate arithmetic, X form for register to register operations, and I and XL form for branching and special registers like the link register and the count register. PowerPC uses simple displacement and indexed addressing modes with optional update versions that help in loops. Hardware registers like LR, CTR, and the conditional registers make branching and function calls very fast and efficient. It also supports AltiVec vector instructions for high performance multimedia and gaming. Overall, the ISA is simple and efficient and optimized for high speed. Now, coming to the data path and pipeline. The PowerPC data path describes how instructions move through the CPU in the stages like fetch, decode, execute, memory access, and write back. It uses a deep RISC pipeline where multiple instructions are processed at once, like an assembly line. PowerPC has separate integer, floating point, load and store, and branch units. And because it is superscalar, it can run several instructions in the same cycle. Many models also support out of order execution, letting the CPU run ready instructions without waiting. Branching is fast thanks to the link register and count register, along with branch prediction to reduce stalls. Overall, the data path is designed for high performance through parallel execution and efficient branching. Now, coming to the memory hierarchy of PowerPC, the PowerPC memory hierarchy keeps the CPU fast by using multiple level of cache. It starts with split L1 instruction and data cache for parallel access, backed by a larger L2 and sometimes L3 cache to avoid slow main memory access. A TLB speed ups a virtual to physical address translation, making virtual memory efficient. PowerPC's simple displacement and indexed addressing modes plus update version of load and store instruction make the array and sequential data processing faster. For multi-core and I/O systems, memory ordering instructions like sync, isync, and AO ensure safe and predictable execution. Overall, fast caches, TLB support, and efficient addressing modes gives PowerPC strong performance in computers, consoles, and embedded systems. Now coming to the specialized features and parallelism. PowerPC includes advanced features that let it handle large workloads in parallel. Its biggest strength is the AltiVec vector engine, which processes multiple data elements at once, perfect for graphics, video, and audio, and game physics. Many chips also include DSP style instructions like fast multiply accumulate for robotics, sensors, and real-time systems. PowerPC supports hardware multithreading used in consoles like the Xbox 360, PS3, and higher-end models provide virtualization through a hypervisor mode for running multiple OSs. It also adopted multi-core designs early. Overall, vector processing, DSP, virtualization, and multi-core support make PowerPC powerful for game, multimedia, embedded systems, and servers. Now, coming to the historical significance and comparison, PowerPC had a big impact by providing that a clean, efficient RISC design could compete with a complex Intel Pentium processor. In the early 1990s and 2000, it powered almost all Apple Macs, giving them strong graphics and multimedia performance. Through features like AltiVec, PowerPC also dominated gaming industries for the Xbox 360, PlayStation 3, and Nintendo Wii, thanks to its parallel processing and predictable speed. But high-end chips struggled with power and heat, making them unsuitable for the thin laptops. While Intel and ARM focused on efficiency, Apple switched to Intel, reduced its mainstream use. Today, PowerPC survives its embedded system embedded systems and as Power ISA in IBM enterprise servers. So I after this I would like to present the code which I have written. So basically the code is it's a popcorn function which actually helps us count how many number of ones are present in the bit version of any number. So, beginning with the first line, the dot text, this helps the assembler, it tells the assembler that the following line belongs to the code section of the program. Now, the dot global pop count, this makes the popcorn function visible to all other files, so it can be called like a normal function. And the dot type pop count at the rate function, this just tells the assembler that pop count is a function and it's not a data. So basically, the I have commented the sections unsigned int pop count and R3 is equal to X just for information purposes. And after this, our function starts. So basically, we this the input number is stored in R3 and we will return in the R3 only after the execution. So the line li R40, what it does is actually load the number 0 into register R4. This will store the number of ones we find in the number. Now at the dot loop starts the loop. Eventually we will be looping through the number. So the loop starts and the dot loop marks the beginning of the loop. Now the next statement compare, which actually compares the register R3 with 0. If R3 is 0, it means we have checked all the bits and we can actually close the program. So from that the BEQ dot done. So the last line would be executed. So coming to the another line that is Andy dot R5 R31. So actually it checks the last bit of the number by performing a AND operation on it with 1. If the result is 1, the last bit was if the result is 1, the last bit was 1. But if it is 0, then the last bit was 0. And the dot means that this instruction also updates the conditional flag. So if the last bit was 0, then it would skip the step where we increase the counter actually. And if not, then you can see that added R4, R41, it actually increases the counter like count plus plus. Now, if the after that, we are actually using the skip increase, which actually this is a label which marks both paths for bit is equal to 0 and bit is equal to 1 when come together. So after that line, we are using SRWI R3 R31, which actually shifts the number in R3 right by 1 bit. So this removes the bit we have checked and brings the next bit into position. After that, the we jump back the loop to the start. The p dot loop actually what it does is it actually makes the instruction move back to the dot loop so that the it would continue to loop through the number. And the dot done label, this label is reached when the R3 is 0 and no more bit remains in the number. So after that, we copy the final count from R4 to into R3, which is done by MR R3 R4 because R3 is the function's return register also. And BLR actually it returns from the function. This actually jumps to the place where the function was called. And the last line, the second last line, the dot size pop count, this tells the assembler how big the function is in bytes. It is used for debugging and does not affect the code overall. And the last line, this is just only the metadata and not the part of the main core logic. So now I would be actually running the code in front of you. So I think I would have to wait a second. I have to share a different screen for right now. Uh, hmm, huh. Debarshi, is it visible? The command line interface for?
Yes, it's visible.
Okay, so basically I have run the program. So coming to the execution of the program, we actually run this command and after that it executes it and then through the QMove we are actually using it. So after that we use this command and we can actually enter any number. For now, I have entered an example in front of you 13. Let's give another example. Let's say I put 100 in it. So actually in 100, actually in the bit version of 100, there are only three ones in present day. And now I would end the from my side and uh, I would like to hand over to Devashi Paul from now. Thank you.
Thank you for such a clear explanation on PowerPC. So just wait a second, I'll share my screen here. Yeah. So greetings everyone. This is me, Debarshi, and I will be speaking. I'll just give a formal recap on what Harsh said just now about PowerPC. So PowerPC actually stands for Performance Optimization with Enhanced Risk. It was developed by Apple, IBM, and Motorola, also called the AIM Alliance. It's a risk-based architecture, meaning it uses reduced instruction set, very efficient, clean, fast instruction execution. It follows a load store design, so only load and store instruction access memory, which makes execution simpler and faster. So what now about PowerPC also supports 32-bit and 64-bit modes, and it was used in a lot of places like embedded systems, automotive ECUs, routers, gaming consoles, and earlier Mac computers used this before they moved to Intel. So talking about the ISA, PowerPC uses fixed 32-bit bit instructions. So why is that important? Because it makes decoding easier and improves pipelining performances. Main latest three type of instructions: D type, immediate; X type, the register ones; and B type for branch instructions. Uh, Addressing nodes are also pretty straightforward here. Register addressing, immediate, indexed, and relative branch addressing. Some cool or interesting instructions I liked here, let me show, like MULW, that's a multi-low word which are used in my factorial code. Also, there are some others like BC, that's branch conditional, which is really flexible for writing if else or loop logic in assembly. Back to the PPT here. The other parts are data part and pipelining. PowerPC normally has a classic five-stage risk pipeline. So fetch, decode, execute, memory, and write back. Pretty standard for risk. But yeah, the advanced PowerPCs like G3, G4, G5, they support superscalar execution, meaning multiple instructions run in the same clock cycle, say G3, G4, G5. Um, In memory, the PowerPC usually has separated L1 into instructions, as said by Hirsch and explained beautifully. Mm, They also support hardware prefetching and write-back cache. Some versions even have ECC for reliability, which mainly used in aerospace, or ECC for reliability and for suburban models. Yeah. Special features and parallelisms include ALTI-VEC, also called VMX. VMX, it's a SMI instruction used for multimedia graphics, signal processing, AI, basically vector operators, very powerful. Now, I will show you a simulation task which I did in VS Code, which is PowerPC assembly for factorial. Let me open the VS Code part here. That's my VS Code terminal. This is my PowerPC assembly code for calculating factorial. So in PowerPC, function arguments I have stored in R3, as you can see, R3. So I take the number n, suppose I want to find the factorial for number 5. So I'll store the number in R3. That's simple. If n is 0, it will just return 1, as I have commented here. If n is 0, it will return 1. So what the code does here is, suppose I load some number in R3, and then I load 1 into R4. So it has to be loaded, some product has to load in R1, in R4 to get the product not 0. Then I decrement R using add here, add R4, R4, R3. So R4, R3 goes. Then using the compare, I compare the branch that it has gone back to a loop, and the value has become 1. This goes again and again till all the numbers, suppose for 100 factorial, 100 times it will go and go and go on. And at the end, we can move back to the result, get the result. We can just see the result here. Uh, Let me open the tab. Yeah, that's the Ubuntu terminal. Suppose, yeah, that's the code for compiling the code I've just written. Yeah, the code just successfully compiled. Suppose I want to find the factorial for 8. That's 8. I've already stored 8 here in the register. So, uh, yeah, that's 8 factorial giving 40320, which is absolutely correct. So this is just a simple C code to call the assembly function. I've also put the codes in my PDF appendix A and the main function in appendix B. So for input A, the output I've shown you successfully. The programs also work properly with QEMU in simulator that I and Hers both have used QEMU. So to conclude, this assignment really helped me understand assembly language for disk architecture, especially registers, load store concept, branching, and multiplication operations. I also learned how to compile PowerPC code using cross compiler and run it on QEMU. So thank you everyone. Thank you Harsh. Thank you sir for taking your time. Have a good day.